All right, hello and good morning. Oh, today is a good day. What up, Diana? Whoa, where's my? There we go. Dude. Dude, the online class morning cup of coffee is clutch. Today's a good day. I don't know how many of you are aware of this fact, but today, whoa! I was doing adult coloring books again. That's why my pen settings are all funky. There we go. Today, well, it's a little thin. Let's go. Yeah. Anyways, today's a good day. Because today, I don't know if you're aware of this, is May the 4th. Which makes it an unofficial Star Wars Day. So anyways, I'm obviously a huge proponent of May the 4th. We've had totally, and in keeping with tradition precedent, we've had class land on a surprising number of theme days here at the end of the semester. And just like Earth Day, just like 420, our playlist has nothing to do with May the 4th. So you can catch our mixtape in the comments. There's the link to the Spotify playlist. It's I don't know where you're all at, but it was like a warm morning, like the kind when you could tell it's gonna be like a hot day, and it was just summer vibes. And so anyways, our daily mixtape is Summer Thrumming. There's some pretty chill beats up in there. Surprising, or not, I don't know, surprising, different mix of things, bands. Kanye West, Beck, Radiohead, and Gorillaz, but all the songs have really, really nice beats to them. That's kind of the unifying theme. And it hit me that we only have 2 weeks of classes, right? This is the second to last week in the semester, the penultimate week. Dude, yeah, there could totally have been some Kendrick up in this playlist. Maybe on Wednesdays we'll get him in the mix. Second to last week of classes in the semester, so we're almost done. We're almost through, and it's been an amazing ride so far. You guys have made it an amazing ride, and I'm kind of sad to close this chapter, but we still got 2 more weeks, stuff to enjoy, and yeah. Kanye is the first one on this. The other K rapper. There's 2 K rappers, right? Well, it's probably more than 2. My brain goes to 2 different ones. But What was I saying? Yeah, we got 2 weeks left. But also I'm starting to feel the crunch a little bit because next week exam 3 is dropping, and then the week after that we have the final, and I'm almost done with the multiple choice for exam 3. I will definitely have more to say about that as I complete the written portion of the exam. Anyways, I'm going to have my head down. I'm going to be working on that hard this week and over the weekend. But anyways, if you have questions about that or want to talk about the test, I can tell you what I know. On the flip side of lecture, it's 11:32, so I think we should go ahead and dive in to today's content. Excuse me. I don't want to speak too soon. My hope is to be able to get some review in, but we'll have to see how this week of lecture goes, and I'll be able to speak with more certainty about our last week of instruction schedule, lecture schedule when we get there. So, without any further ado, let's go ahead and dive in, continue our discussion of hybridization. All right. Now, where we left off on Wednesday of last week, we had seen what hybridization was, or we had, well, sorry, I'd given you the big conclusion, like this is how you assign hybridization, and then we started to unpack where did this come from, what's kind of the theory behind it, and we looked at sp3 hybridization to kind of bridge that gap between orbitals, what we know of orbitals and what we know of the shapes, the geometries that molecules take, what we've learned from Vesper. So hybridization is kind of a way to bridge what we know of atomic orbitals and what we know of three-dimensional shapes. And in our last lecture, which you can rewatch if you haven't seen already, we explored how we mathematically combined our s orbital and 3p orbitals to make 4 atomic orbitals, all right, which were called sp3 hybrid orbitals. And that's where we left things off. And so we were able to use that concept of hybridization to explain the tetrahedral electronic geometry, which was cool. And now we're going to use that same idea to show how you can use hybridization to explain other electronic geometries as well. And we're going to begin this discussion with looking at the trigonal planar electronic geometry with the molecule C2H4. This molecule's name is ethylene. All right. Now, if you draw the Lewis structure for ethylene, again, this is an organic molecule. There's no real central atom in this molecule. But you draw out the Lewis structure, which I'm just going to write really quick. I could ask you to calculate the number of electrons in our budget, make the connections. Oh my goodness. I just whacked my microphone like twice. If you're wondering what that pup is, those are my hands. And that's my 2-year-old in the other room, who I think just finished smearing a yogurt all over his body, so he's quite a happy camper. So here's the Lewis structure for ethylene. I'm just going to draw it for the sake of time. And one thing that you'll notice is as I said earlier, this molecule has no central atom, right? But that being said, we can still label the geometry at each carbon, even though there's no central atom. Each individual carbon atom in this molecule still has a geometry. So if you look at this carbon, for example, if I asked you to label the geometry, you would look at it and realize that this carbon has 3 atoms and no lone pairs, 0 lone pairs, which makes it trigonal planar for its geometry, right? So this is a trigonal planar carbon. And the second carbon is actually in the exact same boat. Both of these carbons are trigonal planar. So if we were to draw this thing in 3 dimensions, right, if we were to draw the 3-dimensional representation for this molecule, it would look like this. We know that trigonal planar geometries have bond angles of 120 degrees. So the carbon on the left would have everything, right, 120 degrees apart. Same with the carbon on the right. So this is kind of the 3-dimensional representation of this molecule. Both of these carbon atoms have a trigonal planar geometry. They have bond angles of 120 degrees. All right, and this is what the molecule ethylene looks like. It's common feedstock for a lot of different polymerizations. Yes, Raj, correct. Both of these. Whoa. Because they both have trigonal planar geometries, they are both sp2 hybridized. Now we know that because we know the electronic geometry determines the hybridization. But what I want to do here is look at, kind of break down the hybridization process like we did for the tetrahedral geometry and see how that hybridization scheme, the sp2 hybridization scheme, gives rise to this 3-dimensional shape. And actually, I'm going to open a new slide because this one's already a little crowded. All right, so just redrawing our molecule up here. So we saw Wednesday, last class, that that when we hybridized with our s and our p orbitals together, when we used all of them to make new hybrid orbitals, that that we could explain the tetrahedral geometry. All right. Now, if we use all 3 of these, actually, Raj, polarity is a different thing. We'll be getting to polarity. We might be starting polarity by the end of today, or if not, we'll definitely be hitting it on Wednesday. All right, so we saw that when we made new hybrid orbitals with our s and all of our p orbitals, that we got sp3 hybrid orbitals, and that explained tetrahedral geometry. So if we used all of our orbitals again in hybridization here, we wouldn't get the trigonal planar geometry that we see in the molecule. Instead, rather than making new hybrid orbitals out of everything, we are just going to make new hybrid orbitals out of our s orbital and 2 of our p orbitals, px and py. All right, that will make 3 new hybrid orbitals. All right, because we used 1 s and 2 p orbitals to make these new hybrid orbitals, we say that they have 33% s character and 67% p character. Oh, sorry. Let's see. Question from Sulai. But is there an exact date for exam 3 and final yet? Not quite yet. Oh, well, Sulai, great question. Let me finish this explanation and I'll circle back to you. Okay. So these new hybrid orbitals are 33% s and 67% p. All right, so they are a hybrid of both. They look more like p orbitals than s orbitals, and these are called sp2 hybrid orbitals. All right, that is what they're called. All right, these are sp2 hybrid orbitals. And you'll notice that they get the p orbitals used to make our sp2 hybrids are px and py. So our sp2 hybrid orbitals are contained in the xy plane. All right, they get all of their directionality from the x and the y orbitals, so they're all kind of contained in that two-dimensional plane. Something to keep in mind, even though we didn't use our pz orbital in our hybridization scheme, it's still there. We've got so this molecule, or these atoms, when they hybridize, have 3 sp2 hybrid orbitals plus an unhybridized pz orbital at their disposal, and they have all of these available for making the bonds. All right, so for their bonding. Now, I am going to, let's see, I'm actually going to rearrange my whiteboard a little bit. Going to pull this down and drop it here. Okay, so let's look at, now that we have seen the hybrid orbitals available to us, they're all in the xy plane. Let's look at how these 2 carbon atoms and these 4 hydrogen atoms bond. Let's look at the bonding systems, the overlap, the direct orbital overlap that they do to make the bonds we see in this molecule. All right, so first, we've got our carbon, and this I'm taking the carbon on the left, and it has, here, I'm going to color code this a little bit better. This carbon has 3 sp2 hybrid orbitals that are all in the same plane. All right? They're all in the same plane, and they all have 1 electron. All right? Now, we know how to make a single bond with hydrogen, right? Hydrogen is going to roll in with its 1s orbital and overlap with the sp2 hybrid orbitals on carbon to make 2 carbon-hydrogen sigma bonds, right? So this is, again, a sigma bond. This is a sigma bond. These are CH sigmas because they're between carbon and hydrogen, and they're formed by direct orbital overlap between the 1s orbital on hydrogen and the sp2 hybrid orbital on carbon. All right, so that explains the single bonds that we see between carbon and hydrogen on the left side of the molecule. Now let's look at the carbon on the right side of the molecule. And this guy I'm going to draw in green. This carbon also has 3 sp2 hybrid orbitals at its disposal, each with 1 electron in it. And we know what those two that I've just drawn on the right side are going to do. They're going to make single bonds between carbon and hydrogen. The third one is going to engage in direct orbital overlap with carbon to make that third sigma bond. So again, we have direct orbital overlap, making 2 more carbon-hydrogen sigmas. But then here in the middle, we have our first carbon-carbon sigma bond. All right, and this sigma bond is made through the direct orbital overlap of an sp2 hybrid orbital on carbon, the blue one, and then another sp2 hybrid orbital on the green carbon. All right, so far in this molecule, we're looking at a bonding system with 5 different sigma bonds. All right, we've got 5 different sigma bonds, and that's a problem. All right, if you look, you're like, why are 5 sigma bonds a problem? Well, there's nothing wrong with the sigma bonds in and of themselves, but if you count the number of bonds in the Lewis structure for ethylene, you'll notice that ethylene has 6 bonds. All right, so the question is, where is the 6th bond? All right, where is the 6th bond? And you're looking at the Lewis structure that I have on the page and the kind of the balloon picture that I have of all the direct orbital overlap creating all those bonds, and you're like, well, right now we only have 1 bond between carbon, but the Lewis structure has a double bond, so we need a second bond there. Right, so the answer to the question, where's the 6th bond, is, well, the 6th one is the carbon-carbon double bond. Right? That raises another question. How do you make a double bond? And to answer that, we're going to need to shift our perspective. Let me show you how. All right, so up to this point in time, I've been drawing this molecule in this perspective, right? It's totally flat, trigonal planar on both carbons, but I'm going to rotate this molecule 90 degrees, all right? I'm going to rotate 90 degrees. I'm going to draw this molecule in a different perspective. I'm actually going to shift this around. I'm going to take this picture that I have, and I'm going to rotate it 90 degrees. Right now, all the H's are in the plane of the board, but I'm going to draw this from a perspective where the hydrogens are all still in the same plane, but it's a plane that is perpendicular to the screen, one in which it's coming out at you and then going back behind the screen. All right, so these two structures that I've drawn are the same. I've just flipped it 90 degrees. So now it might help you visualize to hold your hand up to the screen perpendicular. If you were to put your hand at a perpendicular plane to the screen that you're looking at, that plane that your hand is in is where all the H's are. They're coming out at you, away from, at you, popping out of the screen, and then going away from you back behind the screen. Hopefully you can make that visual connection. All right. The reason why I'm doing this is all 5 sigma bonds are in the X, Y coordinate plane. All right? All 5 sigma bonds are in the XY coordinate plane because they were all made with sp2 hybrid orbitals that came from px and py. But when you look at the coordinate plane, a 3-dimensional coordinate plane, you can see that the z-axis is perpendicular to that coordinate plane. And as I've drawn right there on the screen, you can see the z-axis is in a perpendicular coordinate plane, and drawing the molecule in this perspective will make it easier to see what happens next. All right, so here I'm gonna draw our molecule. I'm not gonna draw the balloon kind of direct orbital overlap bonding pictures for my CHs, for my carbon hydrogen sigmas right now, for the sake of clarity. All right, what I am going to do is draw my carbon sigma because it'll be important. All right, so this is the picture that we had on the previous slide where we had all 5 sigma bonds, right? But we still were missing one more bond. We needed one more, and we know in the Lewis structure that it's a double bond. The question is, what is that double bond in terms of bonding, in terms of orbital overlap? Well, when you look at the orbitals we've used to make these 5 sigma bonds, we've used up all of our sp hybrid orbitals. And that means there's only one orbital left on carbon that has not yet been used, and that orbital is our unhybridized PZ. Each carbon has an unhybridized PZ orbital with 1 electron in it. All right. Now, here's the problem. All right, here's the only orbital on each carbon left available to engage in bonding. And there is no way for these 2 orbitals to engage in direct orbital overlap because they're at a 90-degree angle. They're perpendicular. They're orthogonal to the plane containing all the sigma bonds. There's no way for these orbitals to touch. All right, so for these 2 PZ orbitals, direct overlap is not possible. All right, not possible. So what can they do? Well, it turns out something very special happens when you have 2 p orbitals that are parallel to each other in space. All right? when you have two p orbitals parallel to each other on adjacent atoms, let's see. Oh, Ryan, great question. So the shading, comes from the mathematical solution. Oops. The mathematical solution to the probability calculation. For finding the electron in space. It turns out half of these, the possible answers, have negative values, and so the shading represents the fact that there are both positive and negative solutions to this problem, and the opposite sign for each value is reflected in the shading. Oh, wow. Here, hang on. It's my first time writing a comment that was larger than larger than 200 characters. And the answer is no. You totally do not need to worry about. Worry about it for the test. Totally don't need to worry about it. Yeah, but I do it to be kind of complete, to be correct, but I won't be testing you guys on that. Because those details belong in a different class. Alright, so for these two p orbitals, direct overlap isn't possible, but when you have two p orbitals parallel in space on adjacent atoms, something very special happens. The two orbitals start to blur together both above and below where the sigma bond lies. Alright, they start to blur together, and the barriers between these orbitals start dissolving, and they merge into a totally new type of orbital. Alright? And they make a totally new type of bond. When the barriers between these two orbitals dissolve, they allow their electrons to meet in the middle, and this creates the sixth bond, the second bond between your two carbon atoms. All right. This is something called indirect orbital overlap. All right, so this is indirect orbital overlap. And the type of bond created here is called a pi bond. All right, so this is indirect orbital overlap that makes a pi bond between the two carbons. All right. Now, a couple things to note. You can see that I've drawn the electrons in the top half of this orbital. Something you should be aware of, though, is when I talk about the pi bond has two lobes. All right? The pi bond is both the top half and the bottom half together. Those two things together is I should say, the pi bond. Okay, Sulai, great question. So Sulai just asked, so this only happens with unhybridized PZ orbitals. And it turns out it can happen with any unhybridized p orbitals. They don't have to be PZ. It doesn't have to. Whoops. Involve PZ. And we'll see an example of that in a few minutes here. All right, so a couple things to note. The pi bond is both lobes. Yes. Okay, Sulai, that is absolutely correct. The two p orbitals must be parallel. To engage in indirect orbital overlap. Yeah, absolutely. As long as the two p orbitals, unhybridized p orbitals, are parallel, they can engage in pi bonding through indirect orbital overlap. So again, the two lobes of the pi bond are both part of one pi bond. So when you see these two lobes, those aren't two pi bonds. That's one pi bond together. Also, I've drawn the electrons for this bond kind of up in the top half. But I don't want you to think that the top half is full and the bottom is empty. The electrons are actually occupy both lobes of the bond. They're both above and below at the same time. They're moving so fast that they fill the shape. But now here's an interesting thing. You'll notice there's a gap. There's what's called a node between the two lobes. Like, they don't actually physically touch each other. And what's cool is the electrons actually move from the top lobe to the bottom lobe and back. They're blipping back and forth constantly without traveling through the space in between. They literally go from one point in space to another point in space without moving through the line that connects those 2 points. So they're literally teleporting through space. No, well, not through space. From one point in space to another without traveling through. They're blipping back and forth. They're teleporting. This is a quantum phenomenon called tunneling. So yes, teleportation is real. And before all of the sci-fi nerds, yes, may the fourth be with you, get super pumped for this. We have seen things other than electrons engage in tunneling. Unfortunately, the largest thing ever observed to tunnel has been a proton. So we can't really do this with things and or people like ourselves yet. Then that leaves the door open to all sorts of fun science fiction possibilities. But right now, protons are the biggest boys that can actually engage in quantum tunneling. All right, so the electrons in the pi bond fill both the top lobe and the bottom lobe. And that is our pi bond. All right. Another important thing. It's a very common mistake, common misconception. Okay, let's see. So we need... Yeah, exactly. Raj just said, so we need to shrink to the size of a proton. Yep. We just need to, like... Yeah, Pim Particle, where are you? Yeah, Ant-Man. I know. Well, we just gotta get really tiny, right? We just gotta get really tiny. And then we can teleport. The sad thing is, if we did get that small to teleport, the distance we'd be moving would be smaller than like just our normal physical bodies taking a step. So there's a lot of things we got to work on here, because we could shrink ourselves to move a distance that would literally be within an atomic radius, right? Smaller than we can even see with our naked eye. But theoretically, it could happen. Protons are kind of big. They don't like to tunnel. They don't tunnel often. So really tiny if we want to do this stuff. Okay. What was I saying? Oh, right. Common mistake. Common mistake is, so people learn about pi bonds, right, in the context of double bonds, and a common mistake is to think that a double bond is a pi bond, and that is not the case. A double bond is 1 sigma bond plus 1 pi bond together, all right? A double bond is a sigma together with a pi. A pi bond by itself is not a double bond. It's one bond. A double bond is, you have a double bond in a molecule when you have a direct orbital overlap forming a sigma bond together with indirect orbital overlap forming a pi bond. All right? So a double bond is 1 sigma plus 1 pi. This is sp2 hybridization, and it explains what we see for every trigonal planar electronic geometry. Cool? All right. Let's take a look at sp hybridization. All right? Let's take a look at the bonding system here. So, for example of sp hybridization, we're going to look at the molecule acetylene. And you'll notice that both of the carbons in this molecule have a linear electronic geometry. Each carbon is bonded to 2 atoms, so there's only 2 electron groups, 180-degree bond angles, linear electronic geometry. All right. Now, from a hybridization perspective, we've already seen what happens when we hybridize our s orbital with all 3 p orbitals. All right, and we see we get sp3 tetrahedral geometries. We've seen what happens when you hybridize your s orbital with 2 p orbitals. We get trigonal planar sp2 geometries. Now, for this one, we're just going to hybridize our s with 1 p orbital. All right, so this is going to make sp hybrid orbitals. Whoa, that one's kind of funky looking. All right, so these are sp hybrids, and we only get 2 of them. We use 2 orbitals to make them. We get 2 orbitals out the other end. Just like with our last example, we still have an unhybridized pz orbital, But we also have... Oh, sorry, I wrote PZ twice. We have an unhybridized PZ and an unhybridized PX orbital when we engage in SP hybridization. All right. These SP hybrid orbitals are 50% S, 50% S character, and 50% P character. All right. Now let's look at the bonding in this system. All right. So first, we have our carbon. Whoa, I don't want that to be in yellow. All right, we have our carbon, and our carbon has two sp hybrid orbitals. I can do a better orbital than that. All right, we've got two sp hybrid orbitals. Something to remember is these sp hybrid orbitals only get their directionality from py, so they're on the y-axis. All right, that's why you'll notice they're in a straight line. The only, as we know, s orbitals don't have directionality. These sp hybrid orbitals inherit their directionality from py, and so their only directionality comes from or lies along the y-axis. All right, so this carbon has an electron in each sp hybrid orbital. We can make our carbon hydrogen sigma by overlapping hydrogen's one s orbital with the sp hybrid orbital on carbon. That makes our CH sigma. We are also going to make a carbon-carbon sigma bond by overlapping the second carbon's sp hybrid orbital with the first. All right, our second carbon still has another sp hybrid orbital, and it will make a sigma bond with another hydrogen through direct orbital overlap. All right, so we have our three sigma bonds in place here. All right, now, based on our previous example with a double bond, I'm fairly confident you can what's the word I'm looking for? Totally drawing a blank. Anticipate. There we go. It's multisyllabic. You got to cut me some slack on that one. I'm pretty sure you can anticipate where this is going. You're like, okay, well, with sp2 hybridization, we made a double bond. We used all of our direct orbital overlap options, and then we went and used our unhybridized PZ orbitals to make a pi bond through indirect orbital overlap. And if you're thinking that's what happens here, you are 100% correct. These two orbitals, because they're parallel to each other on adjacent atoms, blur above and below the plane, or sorry, above and below the sigma bond to make a pi bond between our two carbon atoms. All right, so as of this moment in time, we have 3 sigma bonds and we just made our first pi bond. All right, but you'll notice that we're still 1 bond short. In the Lewis structure for acetylene, we have 5 total bonds, right? We've got 2 CH bonds and then a triple between our carbon, and right now in this drawing we only have 4 bonds. So where is the 4th one? And the answer is, we've used, if you look at our orbitals up top, we've used both sp hybrid orbitals, and we've used our unhybridized pz. The only orbital left to use is our unhybridized px. Now, remember your three-dimensional coordinate plane. The y-axis is horizontal in the plane of the screen. The z-axis is vertical in the plane of the screen. The x-axis comes out at you, right? It pops out at coming away from the screen perpendicularly. This is the hardest one to draw, all right? Because our unhybridized p orbitals are coming out of the screen at us. It takes a little bit of perspective drawing. All right, so here's how you do it. And this is where those of you who are drawing in pencil have an advantage to the pen users. Because the lobe of the p orbital that I'm working on now is coming out in front, right? So it blocks out the stuff behind it. And then the second lobe of the p orbital is going back behind, so it kind of disappears behind that top lobe of the first pi bond. We have a second one, right? Second unhybridized p orbital. That again is coming out in front of that lobe of our first pi bond. So we've got it there and there. All right, so that is where our two px orbitals are. Now, these two, because they're parallel, will also engage in indirect orbital overlap. All right, both in front of and behind the sigma bond. All right, the lines here blur. To make a second pi bond. Now, half of this thing is shaded. I'm going to shade the back half. And in the front half, the two electrons that were in our two parallel px orbitals get to meet in the middle, again occupying both lobes, and they form a second pi bond. So now, instead of one pi bond, now we have two. All right, and this is a picture of the triple bond that exists between these two carbons. So remember, one pi bond is here, right? Both lobes together. The second pi bond is here, both this back lobe and this front lobe. All right, just like we said, a double bond is a sigma bond together with a pi bond. Here, a triple bond is one sigma plus two pi bonds. All right, so whenever you see a triple bond, it's made up of one sigma and two pi bonds. Cool. So this is sp hybridization, and this is what that bonding system looks like. One bond formed from direct orbital overlap between the two carbons, and then two cases of indirect orbital overlap. Cool? All right. Any questions about this dude? It can be challenging to draw. It definitely is a challenge, something that takes practice. And it is practice that I would... yes, it is. Yes, it is. Yes, it is. Believe it or not, this is only the second... This is drawing these kind of pictures in perspective takes practice. Definitely practice I would recommend that you get, because these types of problems always end up on exam 3. I ran out of pages. Oh no! Running out of pages in a notebook is terrifying. All right. Okay, so now that you know what sp2 and sp hybridization looks like, I want to do a problem with you. Probably well, let's see. What's our time like? Okay, we got like a half an hour ish. So you may be wondering. True story. All right. You may be wondering, okay, how will this stuff manifest on in an exam context? All right, and they can manifest like this. All right, so let's do an example. I will totally ask you on exam 3 to draw a 3-dimensional representation of the bonding orbitals between carbon and oxygen in, and then I'll give you a molecule like carbon monoxide. All right, and whenever I say draw a 3-dimensional representation of the bonding orbitals, this is when you think sigma and pi. All right, the types of things that we've been doing, showing direct orbital overlap or indirect orbital overlap. I'm asking you to draw that picture. All right, now to do this problem, first, we need to know what the hybridization is, right? We need to know the hybridization of the atoms so we know. Oh, we're going there. We need to know what the hybridization is of our atoms because that will tell us, our hybridization tells us how many pi bonds we need to make, right? If we're sp3 hybridized, we don't have any pi bonds in this situation. If we are sp2 hybridized, we're going to have one case of indirect orbital overlap because we have an unhybridized p orbital. If we're sp hybridized, we're going to have 2 cases. All right, so let's look at the hybridization, for example, of carbon. In this molecule, carbon is bonded to one atom, and it has one lone pair. So that means that it has 2 electron groups. Two electron groups means you're linear, which means you are sp hybridized. All right? When you look at the hybridization for oxygen in this molecule, you're in the exact same position. Oxygen's bonded to one atom. It has one lone pair. So it has 2 electron groups. It's sp hybridized. All right? Knowing our hybridization means that we can start by, and again, in this, I'm only asking you to draw the bonding orbitals between carbon and oxygen. So those are the 2 that we have to worry about. Carbon has one sigma bond with oxygen, right? So we draw that situation. in there. We're going to make our second bond. So we have a... Okay, hang on. Let me back up just a little bit. We know we're sp hybridized. And we also know that we're dealing with a triple bond. All right? Because we know... And... sorry. Sometimes English is hard. So, we're dealing with a triple bond. And here's why that's significant. We know what triple bonds are made of, right? Triple bonds are made out of one sigma bond together with two pi bonds. So we know we need to start by drawing the sigma bond between carbon and oxygen, and that's what I've just drawn here. I got a little bit ahead of myself. Now we need to take care of our two pi bonds, and when we're dealing with sp hybridization, we know we're dealing with an unhybridized pz orbital and an unhybridized px orbital. All right, so we have our one electron in each pz. These two engage in indirect orbital overlap to make that first pi bond, both above and below the sigma. The lines begin to blur between the two atomic orbitals as they become a new bonding orbital. I'm going to shade the bottom half. It doesn't matter which half you shade, as long as one half is shaded. I'm going to show these two electrons chilling up top. All right, there's our first pi bond. Yes. So Vraj, yes. Ish. Vraj's question, do we have to memorize those combinations of sigma and pi? And I said yes. Then I said yes-ish. I mean, yeah, you do, but one of the cool things about this is the hybridization will tell you, right? The hybridization will tell you, because if you're sp hybridized, if you're sp3 hybridized, that means that you have 0p unhybridized p orbitals. So that's means you're going to form 0 pi bonds. If you're sp2 hybridized, that means that you have 1 p orbital unhybridized, and you're going to make 1 pi bond with it. And if you're sp hybridized, that means that there are 2 unhybridized p orbitals, and you will make 2 pi bonds. All right, so yeah, you do need to memorize them, but you could take two approaches to that, Raj. You could just do a rote memorization and like burn that into your mind, or you can look at the hybridization and learn the association between sp3 means you got no p orbitals left over. You've used all of them. No p orbitals left over means you got no pi's. sp2 means you've saved a p orbital to make 1 pi bond. sp hybridization means you've saved 2 p orbitals to make 2 pi bonds. So there's a couple different ways you can approach it. Yeah, totally. And the rest are sigma bonds. Sigma bonds always come from bonding with hybrid orbitals. Pi bonds always come from bonding with unhybridized p orbitals. All right. Totally. All right, now, so we've got our first pi bond down. We need to do our second pi bond, which is admittedly the harder of the two to draw, because your p... Oh, that's ugly. Your px orbitals are coming out of the board, out of the page or screen, towards you, and then behind the screen, away from you. All right, now I'm going to use an eraser to clean this up, because this front lobe of my pi bond blocks out that lower lobe of the first pi bond, because it's out in front. All right, and all right, I need to do some shading to one of my two lobes. I'm going to shade the back lobe and add my electrons hanging out there. All right, and there is the bonding system between carbon and oxygen in the molecule carbon monoxide. We can see that we have one pi bond like so. We have a second pi bond with both of these lobes, and we have our sigma bond right there in the middle. Cool. All right. Now, this is a very challenging picture to draw. Okay. Sulai also asked, dates. Okay, hang on. Okay, so Vraj, Sulai also asked about the exam dates earlier in the lecture. I will answer her question and your question after this next example. So we're gonna do one more, and then we'll talk business. All right. Okay. So let's do one more example. All right. Let's look at the following molecule. And here I'm drawing the Lewis structure. No shape is implied by the Lewis structure. Okay, Sulai, great question. I will, if I ask for it, then yes. I usually do say, like, draw a three-dimensional representation, label pi and sigma bonds. It depends upon the problem. Some problems will ask for it, others won't. All right, for this one, we're going to draw the three-dimensional representation for this molecule. Now, to do that, like we saw in the previous example, it's a good idea to start by labeling hybridization, right? Let's label our hybridization. This carbon has 3 atoms. All right, that's 3 electron groups, which means that we are dealing with sp2 hybridization. If you look at this carbon at the end, same deal, 3 atoms, no lone pairs, that's 3 electron groups, sp3 hybridization. Now, when you look at this carbon in the middle, we have 2 atoms and no lone pairs, which means that the central carbon is sp hybridized. All right, sp hybridized, and you'll see that that'll come in clutch in a minute. All right, and here in this problem, I'm asking you to draw 3D bonding orbitals between carbon atoms. draw three-dimensional bonding orbitals between carbon atoms. All right, so we're not going to worry about the CHs. We're just going to look at carbons. Now, we have a double bond between, I'm going to start on the left side of the molecule and work my way right. So between this carbon atom on the very right and the central carbon, we have a double bond, which means that we have both a sigma and a pi bond, right? We've got a carbon-carbon sigma, and to make that bond a double bond, we need to also add in a pi bond, which will be made using our unhybridized PZ orbital, right? We're getting kind of used to that indirect orbital overlap life. By now, we know that the parallel unhybridized PZ orbitals will blur together above and below our sigma bond to give us our pi bond with two lobes. All right. Gosh, the sigma bond is so ugly. It's bugging me. All right, that's slightly better, not much better. But I'm going to live with that one. So we have the double bond on the left side of the molecule taken care of. Now we need to worry about the right side. Well, first we got another double bond, right? We have another double bond, which means that we have direct orbital overlap between our two carbons to make our sigma, and now we need to make our pi. All right? Before we do that, I want to take a moment and consider our central carbon. All right, our central carbon is sp hybridized, which means that it has, sorry about that. There we go. It means it has two sp hybridized orbitals plus one unhybridized pz plus one unhybridized px orbital. And when you look at the central carbon, right now, at this moment in time, we have used both of its sp hybrid orbitals and its unhybridized pz orbital. So I'm here to ask you, what is the only orbital left on our central carbon that can be used for bonding? And the answer is px. Well, when you go and ask yourself, well, where does px lie? It lies on a perpendicular axis to the plane of the screen. So the only orbital available for bonding right now on our central carbon is its unhybridized px orbital. So if that carbon is going to make its second pi bond, Diana, great question. So Diana just asked, how do we know when to use px, pz, or py? One pi bond. So whenever you have one pi bond, okay, so for the last example, okay, so Diana, technically, you could use any of these orbitals in hybridization, but I find that it's easiest to use unhybridized PZ. So use PZ. Oh, sorry. To make the first pi bond. And PX to make the second pi bond. Technically, you could use any of them, but it's easiest to draw. I find it easiest to draw if you use PZ to make that first one and PX to make the second one. So since we need to make that second pi bond for our central carbon, we're going to use PX. Now, the only way to get indirect orbital overlap is if the last carbon has an unhybridized PX orbital as well. And we know the last carbon does have an unhybridized P orbital, right? Because it's sp2. But in this molecule, that second carbon doesn't have an unhybridized pz. It has an unhybridized px because that is the only way to make a second pi bond. That central carbon has already used up its pz to make its first pi bond. It only has px left. So this is the second pi bond in this system. And you'll notice that these two pi bonds are perpendicular to each other. One comes from PZ, the one on the left, and the one on the right was made from PX. One interesting thing is that because your pi system will be perpendicular to the plane that holds your sigma bonds, the two remaining CH sigmas are in the plane of the board there. So the actual three-dimensional representation for this molecule looks like this. It's just a fun little side. All right, and if we're labeling the bonding orbitals in this molecule, we have one pi there. We have our second pi here. And then we have two carbon-carbon sigmas, one like so, and the other right here. All right, and this is probably visually, as far as drawing bonding systems, the most advanced that we'll get to in this class. This is about as hard of a picture as they come. Usually, sp hybridization is harder to draw than sp2, and this is a weird molecule where you have both sp2 and sp hybridization and having to draw perpendicular pi bonds, but to different atoms. We're using at all. You do not need to label them at all. I find that it helps knowing what they are when you're trying to visualize them. But you do not need to, or I should say, but labeling PZ, PX, etc. is not part of the problem. Totally. Okay, Sulai, why are the last two H's in that plane not like the other two? Sulai, that is a great question. And the answer is, you'll notice if you go back and look at our very first pi bond that we drew. So, oh wait, nope, wrong slide. It's right here. If you go back and look at that very first pi bond, you can see that all of the sigma bonds are in a plane and that the pi bond is in a plane that's perpendicular to the plane holding all the sigmas. All right, and you can see that here. Here, all the sigma bonds are in a plane that's perpendicular to the page or the screen, and then the plane of the screen contains the pi bond. Now, if you go back and look at the picture we've just drawn, for that second pi bond, that pi bond is in a plane perpendicular to the screen because it's made with px orbitals. So that green pi bond is coming out of the screen towards you and back into the screen away from you. And that's why your sigma bonds, your CH sigma bonds, will be in a perpendicular plane to your pi bond. And the plane that's perpendicular to the plane that contains the pi bond is the plane of the screen. Does that make sense? And that's why even when we draw the molecule without the orbitals in it, the two CH bonds on the very right are in a different plane than the CH bonds on the very left. Okay. So this is some very challenging stuff. Visually, it's challenging in a very different way than we've been challenged in this class before. I feel like, okay, awesome. I feel like early on, and like with exam 2, it was very challenging mathematically. Yes, Diana. Balloon animals are like straight up bonding orbitals. Yeah, that is exactly what these things are like. They're totally like balloon animals. You could even imagine like you know how like they make those like arcs in the balloon animals? You could like hold them up and those are the two pi bonds together. That is an excellent way to visualize the orbitals that are holding the electrons and forming these bonds. And balloon animals are a solid way to go. And if I were more talented or maybe had experience as a clown, I'd be able to incorporate that into lecture. Theoretically, if we were all in the same room together. All right, now this stuff is oh, let's see. Maybe your whole childhood was a lie. You thought they were balloon animals. Turns out they were bonding orbitals. This stuff is a different kind of challenge than we're used to in a chemistry class. Usually we think like, oh, chemistry, STEM, math, hard. This is challenging, but from a kind of visualization, three-dimensional pictures, can you see this in your head kind of stuff. A unique challenge, different challenge, but I think a very interesting aspect of the class. This is actually my favorite part of first semester Gen Chem. Now, we won't be doing anything more involved than this. This is kind of the apex predator as far as the challenge goes for drawing three-dimensional representations of bonding orbitals. So you've seen it all. and you've seen the worst. Excuse me. And this is where I'm going to put a pin in lecture for today. But let's talk a little bit. There are a couple of questions that surfaced. Both Sula and Vraj, you guys were asking about exam dates. Yeah. This stuff does stretch your brain in cool ways. I just want to put in one more plug. If you liked this stuff is, you get to do more like this, more visualization, more kind of brain expansion. You get to do more like this when you hit organic chemistry. So if you like this, take OChem. And if you found this challenging and you have to take OChem, come back and review it like right before you start first semester OChem, because this stuff is so foundational for what you're going to be doing that getting reacquainted with it, familiarizing yourself with it again, will put you at an advantage for starting that class. You won't do anything like this in second semester Gen Chem. Yeah, exactly. Jana, it does make them more tangible. And a lot of organic chemistry is about kind of visualizing, and can you make yourself see the shape something will take, because this is okay. Little plug here. This is organic chemistry in a nutshell. All right. This is all of OChem in one bullet. It's all predicated on this this thought. If you understand there's no E in understand. If you understand the shape, i.e. structure, of a molecule, you can predict its behavior i.e. its reactivity. All right. And all organic chemistry is an exploration of the connection between structure and reactivity. So this really, I mean, we've been talking about the shapes of molecules and all that stuff with Vesper, but then this took a shift in not just looking at the shapes of molecules, but what shapes are the electrons in, because changes in bonds are chemical reactions, right? And you'll be exploring in OChem the way those bonds and the three-dimensional shape of those bonds change as they break, as they form new bonds. That's what OChem is all about, and it's awesome. It's awesome. It was so cool for me back in 2005 that I changed from being pre-med to just a chemistry major, because I was like, I just want to do that. That's the only thing I want to do, and the rest, as they say, at least for me, is history. For you all, or some of you, it's your future. Not that you're going to abandon pre-med and become chemists, but at least taking OChem in your future. I'm pumped for you guys. It's the best class I've ever had. All right, now let's talk some business. So exam 3. Exam 3 and the final exam. And I believe both Raj and Sulai, your specific questions were about dates. And give me a second, I'm pulling up the syllabus here. Let's see. All right. Let me look at the schedule. All right. So the plan. Okay. Okay. 1 and 2 were, dude. Heck yeah. It sounds like your brother and I could hang. Okay, so on the syllabus right now, we were slated to have exam 3 on the last day of class. It's okay, man. I literally I opened lecture with that joke. Okay, so we were originally slated to take exam 3 in class on Wednesday, so a week from Wednesday, and then our final exam date is May 20th from 11 a.m. to 12:50. So, and I'm still kind of in process with figuring out. I'm still writing these exams. I'm still figuring out the format of everything. But as of right now, and I'll know more as I kind of make decisions, writing them, and then that will give me a clearer picture of how things are going to look. But as of right now, we are going to keep our scheduled final date. So the final, as of right now, is going to be the normal scheduled final. So that is May 20th, and our final exam time, according to the published final schedule, is 11 a.m. to 12:50 p.m. And as of right now, I still need to check a couple things, but my intention is to keep it like that, to keep our schedule final exam date and time. Now for exam 3, exam 3 was supposed to be on the 13th, so a week from Wednesday. And as of right now, here's what I'd like to do. Part of it depends upon how lecture goes on Wednesday, so next class, and then the Monday after. But we've got one last main thing to really cover, and that is bond polarity, molecular polarity, and intermolecular forces. And my intention, I'd like to be able to knock those out in the next 2 lectures. So cover those on Wednesday and then the following Monday, and then use our last class as possibly maybe a review day rather than covering new content. Again, in the original schedule, I was going to give the exam in class on Wednesday, but since we don't do that, I think what my plan is exam 3 is going to, I'm planning on opening exam 3 on that Wednesday, the 13th. So that's when the multiple choice will open. The multiple choice will open, and the written take home will be emailed out on that Wednesday. And I'm planning on both of those things opening after class. That way we can use class time, one last live stream, kind of as a review session. Oh, no way! That's awesome. That is totally rad. Sorry, I just saw your comment just there. I thoroughly enjoy when I get generational students, like when I get like one sibling and then another one takes them, because usually that means that the first sibling didn't hate me. You never know with the second one because unless they have a younger sibling, and if you get, I've never had 3 in a row, where you get like one and then another sibling and then another younger sibling. But with the youngest one, they take it, they pass, and you don't know, because I mean, some students are nice, but some students, like, you know, leave leave what they really think on Rate My Professor. But you know, when you get a younger sibling from a former student, that that at least that the first one didn't hate you, if they're like to their younger sibling, oh yeah, you should take him. Either that or nothing else worked with your schedule, right? But that's always fun. Okay, so that's the plan as of right now. Exam 3, I'm planning on opening it. Oh, that is so cool. You gotta tell him. Oops. I said, what up? You got to tell him I said, what up? So, as of right now, my plan is to open exam 3, both the multiple choice, and send out the written take-home exams after class on Wednesday. And awesome. I'm opening them up Wednesday, and I'm planning on giving you guys more than 24 hours to complete exam 3. I'm planning on closing everything 5:14 the next day at a minute before midnight at 11:59 p.m. So you'll have more than a little bit more than a day, more than 24 hours to turn in the written exam. The multiple choice will be the same, where you can start at any time during this time frame, but you'll have a limited amount of time to take it once you start the exam. But you could start it at any time. I haven't determined how long it'll be. I'm like 80% done writing the problem bank for the multiple choice, and then I'm gonna move on to writing the take-home test. For the final, I'm still kind of in flux with what I'm gonna do with the final. But what I'm considering is this. I'm considering using so originally our final was going to be the ACS final, right? And which we can't do because that class is a sealed exam. You can't make digital copies of it at all. ACS is super protective about it. So there's no way to administer this thing digitally. What I'm considering for the final is doing it 100% through Canvas, and kind of writing my own multiple choice ACS final exam. That is Raj, give you all an A on the final exam. I would love to, but you'll have to earn it. I would love to give everyone an A on the final. And if everybody earns an A on the final, then I'll be able to. So really, it's up to you. Whether or not everyone gets an A. I mean, the gun who's got a gun, right? So yeah, so what? I can't take bribes. Please may I know for which college this is chemistry. Funny dude. You may. This is Gen Chem first semester. For Folsom Lake College. You can pay me respect, Raj. There is no greater treasure in the world than respect. But for real though. So I'm considering for the final not having a written and a Canvas portion, but running the entire thing on Canvas. And oh, dude, thank you so much, funny dude. I'm happy to help. So you can, so I'm considering doing it all through Canvas, kind of writing, an exam that approximates the length and the difficulty level, of the final exam. The other thing that I'm considering for the final is making it all at the same time. So actually, and I think I can do this in Canvas. I'm not 100% sure, but I'm considering making the final open at our exam time, 11 a.m., close at 12:50 p.m., and you have that time to take the final. So I haven't made that decision 100%, but that is something I'm considering doing. So I'll have more on that as we get a little closer. Next week I'll be able to speak to it with more clarity, because again, as of right now, I'm 80% done writing the multiple choice for exam 3, and then I'm going to start on the written exam, and slowly I'll start taking chunks out of the final, but I haven't started writing it yet, so I don't know exactly the form it's going to take. Cool. So that is all that I have. All I have for now. Are there any fresh last minute questions before before we all bounce. Oh my gosh. I'm happy help. I'm happy to help. Oh my goodness. It's I've noticed I'm not really that bad with typos like when I'm texting and stuff, but the talking and writing and typing chat responses all at once brings out my I don't know what it brings out. I make mistakes when I'm typing. And you'll notice when I'm typing and I'm talking, I become a lot slower in the way I speak. Part of figuring out the online instruction deal. Totally. So if there are any last minute questions out there, hit me. If not, we'll be putting a pin in this. I almost said stream. Stream. We finished up hybridization. We'll be hitting intermolecular forces and molecular polarity on Wednesday, concluding that Monday, and then hopefully that'll leave us with our last class where we can review. You can hit me with any questions you have regarding exam 3, and then after that stream concludes, I'll be opening up exam 3 and we will be off to the races. I hope you guys have an awesome Monday. Again, second to last week of Rona season semester. It's been quite a ride. I think I'll have a lot more, reflection. Do a lot more reflecting once this semester's over. But it's been a unique experience, and you all have made it an awesome experience. So thank you so much for that and sharing this with me. You guys have all been very kind and patient, and I'm pulling for you, all of you. I want all of you to get A's heading in to exam season. All right, so we'll call it a class here. I'll see you all. Oh, question. I'll see you all on Wednesday. So anybody get all of your lecture videos for Chem 400? Funny dude, great question. So here's the deal. So I only before this I wasn't streaming. I was lecturing in a classroom at a whiteboard. So I only started. Let me take a look. Actually, started. Live streaming my lectures Diana, may the 4th be with you. Let's all go watch our favorite Star Wars movie today. Okay. So let's see. When did I start live streaming? I'm going back. My first stream was from March 16th. So funny, dude. I have only been live streaming since the 16th of March, which means that this semester, which means I have an incomplete semester, or incomplete. What's the word I'm looking for? incomplete cache of semester videos. So my lecture videos only go back to the 16th of March for this semester. And I used to not do this, and then coronavirus happened and everybody went online, and so as of right now, that's as far back as the archive goes. But moving forward, one of the things that's changed for me is I've gotten a lot of really good feedback from my students, and they have told me how much they've enjoyed having those lectures as a resource to rewatch. And so it's changing the way I'm going to be doing instruction in the future. Even when the pandemic is over and we go back to in-person instruction, I'm going to continue live casting my videos for the classes that I teach. I realize, funny dude, you may be taking first semester Gen Chem right now, and so this won't necessarily help you in the moment, but in the future, in addition to having the kind of the cachet of previous semesters, of my previous semester lectures, in the future I'll be live streaming from day one for all the classes that I teach. As of right now, I'm going to be teaching it's called Chem 305. It's an intro chem for non-majors over the summer, so I'll be streaming that. And then in the fall, I also will be teaching Chem 400 from day one. So fall semester of 2020 will be the first kind of complete lecture through first semester Gen Chem. That will be on YouTube. It's in its entirety. So yeah, unfortunately, I don't have any earlier lectures, because this was kind of the emergency thing that kicked into gear to adapt to the coronavirus situation, but it's kind of changed my perspective and the way I will be teaching moving forward. So anyways, that's a long answer to your question. Thank you all for tuning in. I'm going to call a stream here, and I will see you all on Wednesday. Later.